We have a 5 microcoulomb charge at the origin, Q5. And then we have a Q3 out here somewhere at some very great distance. It's also positively charged, 3 microcoulombs. And it's out here at some initial distance of infinity. This has a mass of 35 grams, so 0.035 kilograms. It's fired toward the origin from a great distance with an initial speed, V0, of 75 meters per second. So this guy is going to travel and get close to the nucleus, but it's not going to get there. It's going to turn around. And it's going to reach some minimum distance, R min, or R final, if you prefer. And we need to find out what that R final is. We need to find out how close does it get to the origin before it comes to a stop. Alright, so kind of like a max height problem, where you would throw something up and you want to know how high does it go or something. But the difference here is that we cannot use F equals ma, right? Because the acceleration is not constant. Since we have a non-uniform field that's being generated by a point charge, right? This charge, Q3, is moving through the non-uniform field generated by charge Q5. The field is not constant, the force is not constant, the acceleration is not constant, so Newton's laws aren't really going to do anything for us. We have got to use work energy. We've got to say the sum of the works done by all the forces is equal to the change in kinetic energy. Now, we're going to assume in this problem that the only force that does any work is the electric force. And now we need to find the work done by the electric force. So there are 3 ways to find the work done by the electric force. There's F delta S cosine theta, which does not work here because the force is not uniform, everything's not constant. Second way is to use minus the change of potential energy associated with the electric force, and that's going to work. In this case, that's going to be minus Q3 times delta V5, because charge Q3 is moving through the potential created by charge Q5. Right? So that's how you do potential energy. It's the charge multiplied by the potential that it is moving through. Alright, I need to calculate the voltage then, the initial and final voltage. Now the final voltage is KQ5 over that final distance. And I don't know what that is. The initial voltage is 0, because R is infinity, right? R initial is infinity. Okay, so the work done by the electric force is minus Q3 multiplied by KQ5 over RF minus 0. And that's equal to the change in kinetic energy, which is 1/2 mv squared. Oh gosh, I wrote that wrong. 1/2 mv squared minus 1/2 mv0 squared. Now 1/2 mv squared is 0. The final velocity here is 0 because it comes to a stop, it turns around. It's like a max height problem. Okay, so alright, so I've got minus, I'm going to rearrange this, minus k q3 q5 over rf is equal to minus 1/2 mv0 squared. Now, I know K, I know Q3, I know Q5, I know M, and I know V0. I just got to solve for RF. So if I multiply K, Q3, Q5 together, that's minus 9 times 10 to the 9 times 3 times 10 to the minus 6 times 5 times 10 to the minus 6 over RF. That's equal to 1/2 times 0.035 times the initial velocity squared. The initial velocity is 75 meters per second. Okay, so that's minus 0.135 over RF is equal to minus 98.44. And that gives me RF is equal to 1.4 times 10 to the minus 3 meters. Or 1.4 millimeters. Here's my minimum distance.